So, this programming of this ROM, so suppose we follow this convention that a 0 will be represented by the situation when there is no connection and 1 will be represented by the situation when there is a connection. So, this address location 3, so you see these crosses are there, so that means these points are connected. Okay. So, they are, so this 1 is connection. So, this if you to look into these crosses, so they are representing the pattern 1 0 1 1 0 0 1 0. So, when this particular line is selected, since this is a decoder, so at one point of time only one of these 32 locations will get selected. So, when this if the input pattern applied here is corresponding to the address 3, then this line will get selected and this line will be since the crosses are here. So, this is 1. So, this A7 will be equal to 1, A6 will be equal to 0, A5 will be equal to 1. So, at the output we will get the pattern that is stored at the location 3. So, this way we can program the ROM, so that we can, so for some permanent content there. So, we can the permanent storage. So, now even if the power goes, so this these fuses remain. Okay. So, these contacts remain. So, as a result you will be getting the content as it is when you put the ROM into the circuit next time. So, the value does not change. So, you can use the ROM for realizing some combinational circuit. Okay. So, the internal operation of a ROM can be interpreted in two ways. First, as a memory unit that contains a fixed pattern of stored words that we have already seen. The second is for implementing a combinational circuit. Let us take an example. Suppose we want to store in the previous example that I have taken. So, this it can be considered as a combinational circuit with 8 outputs, each being a function of 5 input variables. So, for example, here this A7 is a 5 input function, A6 is another 5 input function, A5 is another 5 input function, A0 is another 5. So, I can simultaneously realize 8 such 5 input functions by programming the ROM. Why? Because if I apply a particular pattern here, okay, then this A7 to A0, so they will be containing the content of this. So, I can ideally visualize it like this, that if I0 to I4, so they represent some input for the function A7, and since this A7 this is equal to 1, so this function outputs a 1 here, but for the function A6, so this is not the case. So, this is equal to 0. So, A6 will be output will be 0. So, if I say that this function A7 is like this. So, this function A7, so it has got the min terms 0, 2, 3, some other min terms are there and 29 is there. Suppose this is the A7, then we can it can be realized like this. So, if you look back, so this so for this so for A7, so 0, 2, 3 and 29. So, if you look into this table, then you will see that 0 for the 0 row, so this cross is there, 1 we do not have the cross, 2 I have the cross, 0, 2, 3 and 29. So, at these points I have got the cross. So, if this input pattern is such that this rows 0, 2, 3 or 29 get selected, then the A7 output will be equal to 1. If the pattern is such that some other output is getting selected from the decoder, then the output of A7 will be 0. So, in some sense I can say that this A7 is realizing the combinational function whose min terms are 0, 2, 3 and 29. So, this is what is shown here. So, let us take another example. So, we want to design a combinational circuit. The circuit will accept a 3-bit number and generate an output binary number equal to square of the input number. So, I have got this 3-bit input. So, A0, A1, sorry, this should be A2. This should be A2, not A1. So, A0, A1, A2. And I want the square of that. So, this number is 0. So, square of that is 0. So, basically I am looking for a circuit where I have got these 3 inputs A0, A1, A2, and it outputs 6 bits. So, B0, B1, B2, B3, B4, B5. So, B0 to B5. So, these are the outputs. Okay. I am trying to design this circuit such that this circuit makes the square of this 3 bit number. Now, this 0 0 0 square of that is 0, 0 0 1 square is 1, 0 1 0 square is 4. So, this is 4, 0 1 1 that is 3 square is 9. So, 0 0 1 0 0 1. This way I make this circuit. Okay. I have to this is that functional table that I have. Now, the knowledge that we have gathered in our combinational circuit design, it says that okay, you have to design 5 different Carnot maps or 6 different Carnot maps and do minimizations, and then you have to draw the circuit using logic gates to realize the function. So, this ROM based realization is somewhat simpler, because what we do, we take one 8 by 4 ROM and these address lines we feed A0, A1, A2, and this in this data line. So, we look into this thing more carefully. If you look into this part very carefully, you see that B1 is always 0. So, I do not need any logic to realize B1. So, B1 is always 0 and B0 is always equal to A0. So, B0 and A0 are same. If A0 is 0, B0 is 0. So, this there is no point storing this B0 and B1 lines. So, I can directly take it B0 B1 equal to 0 and B0 equal to A0. But for B2, B3, B4 and B5, they are dependent on the values of this A0, A1 and A2. So, what we do? We take one A. So, this is the final truth table that I need to store. So, I need to store the truth table for this B2, B3, B4 and B5, because I know B0 is B1 is equal to 0 and B0 is always equal to A0. B0 is always equal to A0. So, if from this table, so if we just draw this one, so it says that for 0 0 0 the output should be 0 0 0 0, 0 0 1 it is 0 0 0 0 like that. So, this is the output. So, what I do, I take one 8 by 4 ROM. So, it has got A0, A1, A2 as the output. So, if I take the 8 locations of this ROM, in the first location it is a 8 by 4 ROM. So, there are 8 locations. In the first location there are 4 bits. So, I stored 0 0 0 0, second also I stored 0 0 0 0, third I stored 0 0 0 1, then 0 0 1 0, then 0 1 0 0, then 0 1 1 0, then 1 0 0 1 and 1 1 1 0. So, this first bit, so that is this bit is transferred to B2. Similarly, the second bit is transferred to B3, third bit is transferred to B4 and this last bit will be transferred to B5. So, you will be getting this function realized. Now, suppose A0, A1, A2 comes as say 1 0 0, suppose it gets 1 0 0. So, if it gets 1 0 0, then my pattern is sorry, this is slightly wrong. So, this is not connected here, rather this bit is connected to B5 and this bit is connected to B2 as it is. So, you see that B5 is the most significant bit. So, B5 is connected. So, the first bit that I have stored here should be connected to B5 and this bit should be connected to B2. So, if I apply the pattern 1 0 0, then the square of that is so this is 4. So, that is 16. Okay. So, that is 16. So, 16 is the pattern is given as 1 0 0 0 0. Okay. So, if I just look into this table, if I look into this table, so this is the so say 1 0 0. So, 1 0 0 the output is 0 1 0 0 0 0. So, that should be the output. So, B4 is 1 and rest of the thing should be all 0. So, So, in this circuit, in this case what will happen if I apply 1 0 0, then this B 5 will be equal to 0. So, in this I have stored this pattern 0 1 0 0 here. So, for I have stored the pattern 0 1 0 0 here, 0 1 0 0 at that location, at location 4. So, when I give the pattern 1 0 0 here, so this location gets selected, and as a result this 0 comes to B 5, this 1 goes to B 4, this 1 goes to B 3, and this 1 goes to B 2. Okay. So, you will be getting like, so 0 1 0 0. So, this is always, all these are always 0. So, which is basically equal to 16. Okay. So, this way you can use some ROM to get the combinational functions realized. Next, we will be looking into other types of ROMs. So, there are different types of ROMs, like the very simplistic type of ROM, they are known as masked ROM. So, they are at the fabrication time itself. So, this is fixed. Then there are some read only memory or PROM, programmable read only memory. So, what is also here, normally we have got a programmer available, is it is a hardware circuitry. So, you can put the ROM there in a slot and apply some high voltage, and accordingly the ROM will get programmed. So, the different locations of the ROM, it will get different values. Then there is erasable PROM or EPROM. So, that is so you can program it by means of applying high voltage, but for you can also erase the content. In case of PROM, so you cannot erase the content. So, that is one time programmable, whereas this erasable PROM or EPROM, so you can erase the content also by exposing the chip to the ultraviolet light for some period of time. And this electrically erasable PROM or EEPROM, so they can be erased with an electrical signal instead of ultraviolet light. So, that way, so you need not take the chip out of the board. So, the chip can be there in the circuit board itself, only you apply a high voltage. So, the chip content will be erased, whereas for EPROM you have to take the chip out and expose it to ultraviolet light separately for erasing it. So, these are the different types of ROMs that we have. There are some other programmable logic devices. So, they come under the broad heading of combinational PLDs or programmable logic devices. A PLD is an integrated circuit with programmable gates divided into an AND array and an OR array to provide AND or sum of product type of realizations. So, in case of PROM, we have got fixed AND array constructed as a decoder and a programmable OR array. We have got PAL or programmable array logic. So, the programmable AND array and fixed OR array, and the PLA where the AND and OR both are programmable. So, this is the PROM type of PLD that we have, where the AND part is fixed. So, you apply the input. So, one of the outputs will get selected. So, that is the fixed AND, and then we have got this programmable OR. So, you connect some of these devices. So, while discussing decoder based combinational circuit design, you have seen this type of structures, where we have got this decoder, and some of the decoder outputs are ORed together. So, for whatever min terms, the circuit output should be 1. So, we have ORed those outputs of the decoder to get the programmable output. So, that same thing is here. So, if you are using a decoder and then the AND part becomes fixed, and you have got the programmable OR part to get the PROM. So, we have got this PLD or this PAL or programmable array logic, where the AND part is programmable, but OR part is fixed, and we have got this PLA, where both AND plane and OR plane, they are programmable. So, we will be looking into this PLA, programmable logic array. So, in case of programmable logic array, the decoder in the PROM example can be replaced by an array of AND gates, and that can be programmed to generate any term, any product term of the input variables. I think there is an example here. So, suppose I have to realize these two functions. So, f1 equal to this and f2 equal to this. Now, so first we look into the product lines that I need. So, I need the line A B bar, then A C, A bar B bar C, then again A C B C and this whole bar. So, what is done? So, this so A B A C, A bar B C and B C. So, these are the 4 product terms that I need. So, this is this is the AND plane, the programmable AND plane. So, these switches that I have that are shown here. So, all these points are programmable. Out of that, so these connections have been made. As a result, on this line you will get A B bar, on this line you will get A C, this line you get B C and this line you get A bar B C bar. And then that so that is about the, so this is the AND plane and this side is the OR plane. In the OR plane, I am connecting the product terms, product lines in such a fashion that their OR will give me the individual function. So, this gives me F1 and this gives me this gives us F1, this gives us F2. So, this AB AC bar A B bar AC and A bar B C bar. So, these 3 points, so they are connected to this OR gate. So, their connections are fused. So, you get this term here and then there is an XOR gate, so that we can do some inversion if needed. Like see here F2, you see that in F2 we said it should be AC plus BC whole bar. So, after getting AC plus BC I need to do a complement and that complementing is done by this additional XOR gate that I have, and here there is a program, there are 2 programmable points or 4 So, you can select either the 0 to come to the XOR gate or the 1 to come to the XOR gate. Since for F1 we do not need the complemented output, direct F1 is necessary. So, this is connected to 0. For F2 I need this complemented output. So, this is connected to 1. So, you get this F1 and F2. So, in the programmable PLA programming table, so we first find out what are the product terms, what are the inputs and what are the outputs. So, this is known as the PLA programming table, and once this is done, we can go for the actual realization. So, for this programming table formulation, first we list down the product terms numerically, then we specify the required paths between inputs and AND gates. Then in the third phase we specify the paths between AND gates and OR gates, and then for each output variable we may have a true output or a complemented output for the programming the XOR gate. So, that is how this is done for the programming table part. Sometimes it is better that we do a more careful investigation to see whether I can reduce the PLA size further. So, it may so happen that if I complement one of the output, then there may be more commonality between the product terms of different functions. Since the AND plane is realizing all the product terms, so if I can get a situation where these product terms are less, so I will be getting a better realization. So, this what is done is it is like this. Suppose I have to realize these 2 functions F1 ABC, which has got the main terms 0, 1, 2, 4 in it, and F2 has got ABC, which is 0, 5, 6, 7. The 2 functions are simplified in the maps as is shown here. Now, while doing the simplification, we try for both F1 and F1 dash. Okay. So, for F1, so if you group with the 0 1 element, so you will get A bar B bar, like if you combine these 2, so you will get A bar B bar, then this A bar C bar. So, combining this one and this one, you will get A bar C bar and you will get B bar C bar by combining these 2. On the other hand, if you group in terms of zeros, so which you are getting A B, like say here this is A equal to 1 and B equal to 1. So, these 2 term you can get. So, if you are so this A B will be coming like so this is basically the complement of this. So, if you complement it, then this function will come. So, if the 0 elements are taken into consideration, then you will be getting this like here AB plus AC plus BC whole bar, that is the function we will get. And similarly, here for F2 also you will get AB plus AC, and if you are taking F2 bar, that is then you will be getting the other function A bar C plus A bar B plus A B bar C bar whole bar. Now, what we do is that we compare all these functions and try to figure out the common terms, and we see that if I choose this complemented form of f 1 and true form of f 2, then this a b and a c. So, these terms are becoming common. So, I will so as these terms will become common. So, I can just take them together and get it realized. So, the less number of product terms will be sufficient for realizing this thing. So, we do it that the both true and complement of the functions are simplified in sum of product form, and we can find the same terms from the group terms of the functions f 1, f 1 dash, f 2 and f 2 dash, which will make the minimum number of terms. So, we find that f 1 should be taken in complemented form and f 2 should be taken in true form to get the minimum sized minimum number of product terms. So, that is done here. And final PLA implementation turns out to be like this, that we take these terms. So, that this is simple. So, this term realizes the product term A B. So, this A and B. So, those two lines are switches are burnt. So, this A B comes here. Similarly, A C comes here, B C comes here, and then after doing the XOR, after doing the OR plane here, then we select this XOR programming point. So, that for f 1 I get f 1 bar and f 2 comes directly. So, this way we can have PLA implementation of this circuit. So, then this programmable array logic. So, this is another programmable device where we have got this AND plane fixed. So, this AND the OR plane is fixed and the AND plane is programmable. So, in the OR plane you can get OR of these 3 AND gates. So, you cannot choose any other one, whereas while drawing this AND gate, so you can program all these points to select the inputs that should come for the first AND gate. So, this OR gate is fixed. So, this is the OR of these 3 inputs, these 3 AND gates. Similarly, second OR gate is the OR of these 3. Now, you can select so these first 2 lines, they correspond to I 1 and I 1 bar, second 2 lines correspond to I 2 and I 2 bar. So, sometimes we take this f 1 back and this f 1 and f 1 bar, that is 2 additional inputs that comes back here. So, that is sometimes helpful if there is a sharing of function between f 1 and something else, then you can pass it through these lines and use it on the lines 9 and 10, and that can be used for AND gate connection. So, we will see that. So, essentially in the PAL device, so this OR part is fixed and the AND part is programmable. So, Boolean functions must be simplified to fit into each section. So, you see that if you in a case, so if you need f 1 as a function which requires more than 3 product terms, then I cannot fit it. Similarly, if f 2 requires more than 3 product terms, I cannot fit it standalone. Of course, what you can do possibly if you is that if for realizing one function, if you require more than more product terms, then you can break it down into 3 product term cases and then additionally use some OR gate at the output of those 2 and OR them together. But that is costly, that is some additional gate will be necessary. So, that way it is restrictive. Unlike PLA, product term cannot be shared among 2 or more OR gates. Therefore, each function can be simplified by itself without regard to common product terms. So, this is from the simplification point of view. So, this is easy. So, we do not need to compare between the product between the functions to see whether there is a commonality of product terms between the functions. So, we can simply take individual functions separately and we can minimize them so that they go to one of the alternative. And the output terminals are sometimes driven by 3 state buffers or inverters. So, that is also done so that we can get the inverted output. So, let us take an example. Suppose W A B C D is this one. So, W x y z. So, these are 4 functions. So, we try to simplify the 4 functions like this. So, W equal to A B C bar plus A bar B bar C D bar, x equal to A plus B C D, y equal to this and z equal to this. Then after doing this, we find that first 2 terms of z are same as W. So, this we rewrite it as W plus A C bar D bar plus A bar B bar C bar D. So, after doing this rewriting now, now we are satisfied because individual functions, they are having at most 3 product terms. Okay. So, previous this particular expansion of Z, so that was problematic because it was requiring 4 product terms. So, but here it is requiring 3 product terms only. So, if it was if some line is requiring more than 3 product terms, then we can take a dummy output, and the dummy output can be fed as input for the next one. So, I will come to that. First of all, so this realization, so Z has 4 product terms and we can replace by W. So, here like this. So, this way we can make it simplified, and then the realization becomes like, so W line is connected back and it is connected to this this 9 and 10 lines, they carry W and W bar lines and they can be used for connecting to Z. So, this way we can have a PAL implementation. So, this fuse map that tells like how are you going to connect. So, this product line, so this is A, B and C bar, so that is connected to this AND gate. Similarly, this A bar, B bar, C, so that is connected to this AND gate, and this AND gate is not used at all. So, since it had only this function had only 2 product lines. So, this AND gate is not necessary. So, this is not programmed. So, all these connections are open. Then for the second one, again the same thing, I have got connections, but third AND gate is not necessary, all fuses are intact. So, it is always equal to 0. So, this way we can do the connection, and this W output, so it is fed back to this W and W dash lines, and this W and W dash this W line is used here by the Z output as another AND input to this OR gate. So, that way we can do this realization. Now, if there are if you get some function which is having more number of product terms, then what you can do is you can take a dummy output, like suppose I have got a function f consisting of the product terms like AB plus AC plus say AD plus BC, say something like this. Then what you can do, you can have one such you can take a dummy output, so f dash so let us call it f1. So, f1 is say AB plus AC plus AD, and then f2 is f1 plus BC. So, you can break it down like this and use this type of feedback connection for realizing this. So, for this by this first set you realize f1, and this f1 is fed back here, and then by the second set you realize f2, that is equal to f. So, f2 is equal to f, and this f1 plus bc is realized by that. So, this way you can utilize this back connections, okay, so that you can have functions with larger number of product terms realized. But of course, it is restrictive in the sense that the device that you are using may not have a large number of such back connections available. So, you may not be able to realize very large functions with this type of logic.